Hello students! So this is Donna Nelson, Chemistry 3053, and we're going to be discussing Chapter 6 today. We're going to start Chapter 6 now. And so Chapter 6 is going to be on chemical reactivity and some mechanisms. So first we'll look at enthalpy, the enthalpy and also the entropy of reactions. The enthalpy is the heat energy exchange between the reaction and its surroundings. So you can think of this as the reaction. Sometimes in this chapter it's called the system. And so when it talks about the enthalpy of the system, it's talking about the enthalpy of the molecules. And so when it talks about the enthalpy of the surroundings, it's talking about the enthalpy of the solvent. So just to clarify that. So here we're talking about breaking a bond. And so what happens when we're breaking a bond, you can think of it like this, as there are two electrons in a bonding molecular orbital, and this is representing the bond. And when this bond breaks, one electron is promoted to one atom that was involved in the bond, and the other electron is promoted to the other atom that was involved in the bond. In this chapter, we're only going to be discussing this sort of bond cleavage in which one electron goes with one atom and the other electron goes with the other atom. And here, the electrons have to receive enough energy to be promoted to these higher energy levels, and that enables the bond to break. So obviously, we're going uphill in energy here, and we're going to discuss more about this in just a moment. So here, what I was just talking about is this sort of bond cleavage where one electron goes with one atom that was involved in the bond, the other electron goes with the other atom that's involved in the bond, and this is called a homolytic bond cleavage. It's called homolytic because here the two fragments that are produced are alike in that they're both radicals. They each have one unpaired electron. Now, in the past, we have been talking about heterolytic bond cleavages, those reactions, and in the future, we will discuss mostly heterolytic bond cleavage. And in that sort of reaction, both electrons that are involved in the bond go with one atom or the other. And so here you can see both electrons in the bond going with Y to create an anion, and X is left electron deficient, so it becomes a cation. This is called heterolytic bond cleavage because the two fragments that are created are different. One's a cation, the other one is an anion. In this chapter, we're going to be considering homolytic bond cleavage. So you need to keep that in mind in order to understand what we're doing. The bond dissociation energy, sometimes abbreviated BDE or delta H for bond breaking, corresponds to this sort of bond cleavage, the homolytic bond cleavage, where the bond is broken, one electron goes with one piece, the other electron goes with the other piece. So when you see BDE, it's talking about this sort of bond cleavage. And the tables that you'll see in this chapter refer to homolytic bond cleavage. Most reactions involve multiple bonds breaking and forming. And if it's an exothermic reaction, the energy gained by the bonds formed exceeds the energy needed for the bonds to be broken. And here, what happens there is the products will be more stable than reactants. In an endothermic reaction, it's the opposite. The products are less stable than reactants. So you're going uphill in energy. And here, what's happened is the energy needed for the bonds to be broken exceeds the stability gained by the new bonds being formed. So this is one of the tables, or this is part of one of the tables that you have in your chapter. So here, this is bond dissociation energies, and these are grouped nicely: bonds to hydrogen, carbon-carbon bonds, and a few halogen-halogen bonds. There are a lot more bonds and their energies given in this table, and you'll have to refer to those in working some of the problems. But in each case, this is always talking about a homolytic bond cleavage. So the bond that's in red is the one that's being broken homolytically. So over here, there's not much question here, but here you can see that this is methyl-methyl, and the bond being broken is in red. This is methyl-ethyl, bond being broken is in red. So we're not talking about breaking one of the CH bonds here. We're talking about breaking the carbon-carbon bond that's in red. Here, this would be the carbon-bromine bond that's represented by a red line, is the one being broken. And these are the energies that corresponding to the bonds being broken. And so we will be using those in a couple of the reactions that we'll calculate for. So in the enthalpy, calculating the delta H, the sign of delta H indicates whether the reaction is exothermic, that means energy is given off in the reaction, or endothermic, which means that energy needs to be put in order for the reaction to go. An energy diagram, which you will need to become familiar with, and you may already be familiar with it, is often used to describe the kinetics and thermodynamics of the chemical reaction. The potential energy, abbreviated PE often, is described by the y-axis going up and down. The reaction progress is described by the x-axis going left to right, and it's called reaction coordinate. And the reaction coordinate could be a bond length, it could be a bond angle, it could be a dihedral angle or a torsional angle. And so here what they're talking about is they're talking about the energy, how the energy increases as the bond, the interatomic distance is increased, or as an angle is compressed or increased. Or if it's a dihedral angle, it would be the energy increase as the two groups are rotated relative to each other. So we'll see a lot of those, and you'll see a lot of those during the semester. So here's a couple of them right here. So this is the energy going up, as you can see, and here's the reaction coordinate. Usually the reaction coordinate corresponds to stretching the bond, breaking the bond, a bond. And so this reaction coordinate will correspond to breaking, to the energy change as that bond is broken, or as those two atoms that were involved in the bond move apart from each other. And so here, notice that this reaction is exothermic because the starting materials are higher in energy than the products, so the energy goes up and then it comes down. So energy is given off, the products are lower in energy, energy is released, potential energy is converted to kinetic energy, the delta H naught is negative, so that's this right here, the difference between the bond energies of the starting materials and the bond energies of the products. And the temperature of the surroundings will increase because this energy will be transmitted to the solvent. Here, the products are higher in energy, so you've got some bonds being broken in the starting materials, new bonds that have been formed in the products. And so the energy is consumed from the surroundings, so from the solvent. This is endothermic in that energy is taken up by the reaction. Delta H naught is positive, indicating that you're going uphill in energy. The temperature of the surroundings decreases. And so these are opposites, and you can see here by them being positioned next to each other, they're very easy to compare. Now, this is a problem that's worked in the textbook. Using table 6.1, it looked up the energy of each of these bonds that in the reaction that was being broken. So here, what you had was a carbon-hydrogen bond being broken, a chlorine-chlorine bond being broken, a carbon-chlorine bond being formed, and a hydrogen-chlorine bond being formed. And so what you can see is that these two up here are the reactants, the two below were the products. And so the CH bond is being replaced by a carbon-chlorine bond. And here are the energies as they are looked up from table 6.1. And you can see that here they are added together. The bonds broken are here, positive numbers. The bonds formed are over here, negative numbers. And so the bonds being broken, it's going to cost energy as you go uphill. And so these two are added together. Over here, these two are added together because when the bonds are formed, the molecule becomes more stable. So the molecule goes downhill in energy. And so you simply add these together and you get a minus 138 kilojoules per mole overall, and so delta H naught is negative. It means that the reaction is exothermic. So you can work through this by adding these up, and it will tell you which, whether you put a positive sign or a negative sign in front of each value. So here are the values, and you have to decide whether you're going to put a positive sign or a negative sign in front of each one, because you'll look at it and you'll say, well, this bond is being broken, so positive, positive. This bond is being formed, so negative, negative. If a bond is broken, you're going to go uphill in energy. If a bond is being formed, you're going to go downhill in energy. So you put a negative sign if it's downhill, a positive sign if it's uphill, and then you add the whole thing together. So here's another problem that is worked. And so here you're replacing a CH bond with a CBr bond. So you're going to break a CH bond and a BR bond. You're going to form a CBr bond and an HBr bond. And this is analogous to the previous question. So once again, the bonds broken are going to be positive. The bonds formed are going to be negative. So you have the negative sign here that will go in front of this, and the negative sign goes in front of this. And then you simply add the whole thing up together. It's the equivalent of 590 minus 653, and that equals minus 63, which is exothermic. And so this is a second example. You can work through this, go along with your textbook and work through it, and I would recommend that you do. So this reaction is exothermic also. So it's overall downhill in energy. It gives off heat. Exothermic and endothermic reactions can occur spontaneously. Most reactions that we use are exothermic. If it's endothermic, then you have to, it would be very difficult to use anything in industry where you would constantly have to put energy in. It would be an expensive synthesis. Entropy can be described as molecular disorder, randomness, or freedom. It's actually, you can also think of it as the number of vibrational, rotational, and translational states into which the energy of the compound is distributed. So you're going to have a number of ways of looking at entropy. Here's another one. The gas, when it's in this closed system and you open it up, it will spontaneously expand. Remember, nature works towards lowest energy and highest entropy. So the molecules will expand into a more random system where they are spread out more. Over here, it's less random, more ordered state. And so this one is favored and happens spontaneously. So as you increase the volume, the number of states the molecules can spread across increases. This has greater entropy than that. Potential energy change will determine whether a process is spontaneous. So the total entropy is equal to the change in the entropy of the system. That's going to be the reaction. In our case, the actual molecules, and here the surroundings, will be the solvent in our case. For chemical reactions, this is going to be the, like it says here, the reaction, the molecules, and the surroundings. Now, this is a very common way to look at entropy, probably the most common that you'll be looking at. And here you have greater entropy if you have fragmentation. So here, 1 mole of reactant goes to 2 moles of products. Here you start out with a more ordered system, less ordered system. So this is going to be favored entropically. So here you're working towards higher entropy. Here, similarly, when a cyclic compounds become acyclic, you're breaking the bond. It's sort of similar to this. There's still the two atoms, X and Y, are tethered together, but still this is cyclic, this is acyclic, and so this is going to increase in entropy as the reaction proceeds. So Gibbs free energy, delta G, includes the entropy factor here. So Gibbs free energy includes enthalpy and entropy. Here, this reaction is spontaneous. You have butadiene reacting with ethylene to give you cyclohexene. It's spontaneous. The delta G must be negative. We know that the delta S will be negative because you're working towards a more ordered system. So the entropy is going to be negative. The entropy itself is decreasing. So this is actually going up in the free energy, because if this is going to be negative, then minus T delta S overall is going to be a positive number. So this, in order for this to be spontaneous, the delta H has to be negative in order for this to be negative overall, because this negative number will have to offset this positive number. So you'll be able to tell certain things like that. The Gibbs free energy, you can do reaction coordinates and free energy diagrams, just like we did for the potential energy diagrams using the H, the enthalpy. This is analogous. The ones that we did previously were for potential energy. This is for free energy. The reaction coordinates will stay the same. Usually they are bond lengths or interatomic distances plotted here. So you would have an interatomic distance and the energy of the molecule with that interatomic distance. Then you would move the atoms a little farther apart, and the energy would be a little higher. Then as the atoms move a little farther apart, the energy continues to increase. And so that is how this is literally calculated. These things are done by calculations, computational chemistry. And so that is literally how these diagrams are created. And so here, this is going down in energy instead of exothermic. This, since we're using the Gibbs free energy, it's called exergonic, okay? Because this exergonic in free energy corresponds to exothermic in enthalpy. So you can sort of relate those two words in your mind, So this is what it's called if you're considering the free energy, and this is going downhill. This is negative. If the opposite is taking place, if you have a positive delta G, if the reaction is uphill and you're considering the free energy, this is called endergonic. And so that would correspond to endothermic in the enthalpy, if you're considering enthalpy instead of free energy. So in your mind, you can relate endothermic with endergonic, although one is describing the enthalpy and the other is describing the free energy. So if you relate those two, it may help you remember them a little better. The words are a little bit similar. And so here, this is a reaction like this favors the reactants because the reactants are lower in energy, the products are higher in energy. Okay? And so that finishes the first 3 sections of chapter 6. And so this is the end of the first video for chapter 6.